Hello everyone. So in the last lecture we discussed about the pressure volume work. We took an example of an ideal gas confined in a cylinder, and we said that how work can be done by the system or work can be done on the system. And we took some examples of this work done, how we can quantify this work done by taking into account of the pressure associated with the volume change. So in this class or in today's lecture, we will discuss something more on that, and we will first introduce you to the first law of thermodynamics. Now let us first begin with the relation between heat and work, which is known as mechanical equivalence between heat and work, because as you know, both heat and work are two forms of energy, but they can be interconvertible. Let us first take an example and then we will discuss what is known as Joule's experiment, which was demonstrated by James Prescott Joule. Now before we discuss Joule's experiment, let us conceptually try to understand how we can increase the energy of a system. Now suppose we have a system which is 10 gram of water initially kept at say 25 degrees centigrade, and now we keep this system which is 10 gram of water inside another bath of water which is at higher temperature. Let us say the temperature here is 70 degree centigrade and the mass of the water in this bigger bucket is 100 gram. And suppose after some time, of course heat will flow from the surrounding means here the immediate surrounding is the water which is outside, and the water which is inside the smaller container is our system. So from surrounding heat will flow freely and raise the temperature of the system, which is the smaller bucket of water. Now suppose that the surrounding loses the temperature by 1 degree, which means the final temperature of the surrounding goes to 69 degrees centigrade, which means since the mass of the water in the bigger bucket is 10 times than the mass of the water in the smaller bucket or smaller container, so equivalently you can say that the rise in temperature will be 10 degrees centigrade for the system. This comes from the equation for heat change, which we know already, that heat change will be mass into specific heat into change in temperature. Now since the specific heat is same in this case, that both are water, so the amount of heat change will be only proportional to the mass. So if the heat change is fixed, so same amount of heat is going from outside to inside, so the surrounding lose heat by an amount of Q and the system gains heat by an amount of Q. So Q is also fixed, so delta T should depend on the ratio of masses. So in this case, if the surrounding loses the temperature by 1 degree, the system will gain the temperature by 10 degree. So the final temperature will be 35 degree centigrade. Now this is an example when the surrounding loses heat and the system gains the heat, and in the process the temperature of the surrounding drops by 1 degree and the temperature of the system is raised by 10 degree. Now Joule asked a question. He asked, can we do the similar change for the system meaning starting from say the system at 25 degrees centigrade, we are going to a final state which is the system at 35 degrees centigrade. However, not by directly heating the system just like the example we said, but by doing some mechanical work. So, Joule came up with a very nice setup. What he did, let me first draw the apparatus which Joule designed. So, here he took a similar bucket of water, and this bucket is now connected to a wheel, and the part of the wheel is immersed in the liquid water which is our system, and there is a paddle which can rotate, and this rotation of the paddle will increase the temperature of the system by some amount, which we can measure with a thermometer which is dipped inside this water. So, connected to this wheel is a mass of say m. If the mass falls down from a height, that will create a pull in the or tension in this wire, and that will make the wheel rotate, and that will eventually make this paddle also rotate in some direction, let us say in this direction, and that will eventually increase the temperature of water. From that, Joule concluded that the work done, which we wrote as minus mgh, or which was equivalent to a pressure volume work in our example of the gas inside a cylinder, is also equivalent to some heat change associated with the process. In this case, work is done by the surrounding because mass is falling, and then that work done is being converted into some amount of heat which is increasing the temperature of the system by some finite amount. So, this is known as mechanical equivalence between work and heat. Now, the interesting thing with this example is that we went from the same initial state to the same final state in these two examples. The initial state was 25 degrees centigrade and the final state of the system was 35 degrees centigrade, but we showed that we can either do it by supplying heat directly, just as we discussed in the example with the hot water bath, by immersing the system in the hot water bath, or we could have done it, which we are showing here, is by supplying some amount of work which is being converted into the heat. Now, in the earlier class we discussed about the two-stage cyclic process, where we said suppose we are going from some initial stage to a final stage by single step expansion, and then we are coming back with single step compression. Now, let us try to understand how this pressure volume work, which we already calculated for this process, is related to the heat changes in the surrounding. Now, before we discuss, remember that when we are discussing the properties of heat and work, we said this change in heat and work during a process or during some transformation is across the boundary, and we always measure it, we always measure this change by some effect in the surrounding. So, we are going to now discuss what is this effect in the surrounding. Now, let us consider a cyclic process where we start from the initial state of say pressure P1 and volume V1 to a state which is pressure P2 and volume V2, but then again we come back in the second step. So, the first step we can think of, if the pressure P2 is less than P1, so the first step is nothing but an expansion step, and the second step is nothing but a compression step. So, this is a cyclic process, and at the end of the cyclic process the system should come back to its initial state. But we already know that the surrounding does not come back to its initial state, and we described why this is so by drawing the pressure volume work in the PV diagram, where we showed that if we start with an initial pressure P1 and volume V1 and then change the pressure, final pressure to P2 and volume V2, then the opposing pressure associated with the first step should be equal to P2, and the change in volume in this case is V2 minus V1. So, the work done by the system, because the system in this case was expanding, it was the area under this curve. However, if we go back or want to restore the system in its original state, we have to now set the opposing pressure to be equal to P1, and now the associated volume change will be final volume minus initial volume, which is V1 minus V2. Now, this will be area under this entire region. So, the difference or the extra work done by the surrounding is this area, which mathematically we can write as W1 plus W2 will be nothing but, if we write it in this way, P1 minus P2 into V2 minus V1. So, we just wrote this second equation as plus P1 into V2 minus V1 and then added with the first equation. So, this is the total work done by the surrounding on the system, and you can see that, or this is basically the net work done by the surrounding on the system, and you can see this is a positive quantity because V2 minus V1 is positive and also P1 minus P2 was positive. So, the surrounding does some work. Now, the system is restored to its initial condition, but the surrounding was not restored to its initial condition because we spent some work on net. Now, the question is what happened to this work, because this work must be utilized by in something, in some process. Now, since the system has been restored in the initial state, then we must conclude from here that the temperature of the surrounding must be increased. Now, you can have a feeling of this process, how the temperature of the surrounding has been increased. So, in the initial step, we suppose had a mass M1, and this M1 was chosen in such a way that it creates a opposing pressure which was P2, because remember that initially the expansion was done against the opposing pressure P2 and this was the work done. Then this mass was lifted, and then what we did, we took out this mass M1, but put another mass which is M2, which must be a heavier mass than M1 and which is equivalent to some opposing pressure P1. Since P1 is greater than P2, M2 must be heavier than M1, and that caused a depression and the piston came back and the system was restored in its original condition. So, in this process what we saw that a lighter mass M1, I am using 1 and 2 notation to understand, to describe the process, the first step and the second step. So, it was lifted to higher altitude and then a mass which was already in the higher altitude actually was fallen to a lower altitude, which means since M2 is greater than M1, a net amount of mass M2 minus M1 actually has fallen in the surrounding, that must be converted into the temperature of the surrounding. Remember that it cannot increase the temperature of the system because we have come back to the same initial state of the system. So, the temperature of the surrounding has increased, and this is according to Joule's law, so which we just described. So, according to Joule's experiment, the temperature of the surrounding in this case must have been increased. Now, let us try to understand what we just discussed, and based on that we will build up the concept of the first law as well as the concept of energy. So, what we discussed is that this work which we just did, a net work, was destroyed completely and we got an equivalent amount of heat. Now, in any cyclic process, that means the work done will always be equivalent to the heat withdrawn in the cyclic process. Now, cyclic process means this is with respect to the system, because everything we are working on is the system. So, cyclic process means the system is undergoing some initial change, but it comes back to its original state, pressure which are designated by some pressure, some volume, some temperature. Now, in this cyclic process we can write it as a cyclic integral of the work done. Now, remember that work done. Now, what is dW? dW is the differential work done in every step. Now, remember that it depends on the path of the transformation. What does it mean? If we do the work done in different way, for example, we already discussed that we can go from state P1 V1 to a state P2 V2 by single step. In that case, the work done will be nothing but the area under the curve. Or if we had gone through another path where there was an intermediate step where the system first goes from P1 V1 to P prime V prime and then to P2 V2, then in the first step the work done will be the area under this curve, and in the second step the work done will be the area under this curve. So, the two areas will look like this. In the single step it will look like this, in the two stage case it will look like this. This already we discussed in the earlier class. However, the point here is the amount of work depends always on the path of the transformation. So, it does not depend on the what is the initial state and what is the final state. So, work is not a state function of the system, work is a path function. The amount of work done by the system or amount of work done by the surrounding on the system depends on the particular path of transformation. And in this way we already, and along this way we already discussed that if we do it by single step or two step, the amount of work done is different. Mathematically it means that dW is not an exact differential. By exact differential we mean that a differential which does not depend on the path. However, since dW depended on path, it must not be an exact differential, or sometimes we call it as inexact differential. To denote a difference between exact and inexact differential, we will write this instead of dW, we will write it as d cross W. Some textbook write it as del W. So, this whenever we write this cross, that means actually that this differential is not an exact differential. Similarly, the heat withdrawn will also be an inexact differential because work is just converted into heat. So, if work depends on path, the heat will also depend on path. Now, we have a problem here in the sign convention. Since we are saying that the work done by the surrounding should have a positive sign, that means equivalent to that will be a temperature increase or decrease in the surrounding. If work is done by the surrounding, there will be a temperature increase for in the surrounding, either in the surrounding or in the system. So, we will maintain a negative sign here just to make consistency in our earlier definition that work done on the system is always positive and work done by the system is always negative. So, any work done in the surrounding will be equivalent to the heat withdrawn by the system or heat produced in the surrounding, but we are maintaining this negative sign just to make consistency in our definition of work done. Now, if you proceed with this equation, which is cyclic integral of the differential of work done is equal to negative of cyclic integral of the heat withdrawn from the surrounding, we can combine these two things and write d cross w plus d cross q is 0. Now, we got a very beautiful thing. What we see here, although d cross w individually depends on the path of the system, d cross q also depends on the path of the system. If we take their addition, that does not depend on the path of the system, that will be always 0. So, 0 means whichever path we take, since it is always 0, that means their combination, that some differential has to be a state function which does not depend on the path of the system. That state function we call it as du. We are not writing here a d cross q because it is a state function which does not depend on the path of the system, and we simply write this equation that cyclic integral of du is 0, where u is called the energy of the system, or more accurately u should be called as the internal energy of the system. We will discuss why we call it as a internal energy. Now, we can combine these two relations. What we just got, we just saw that du is nothing but d cross w plus d cross q. So, this is the first law of thermodynamics written in its differential form. So, we started with the logic that work and heat are path functions which depends on the path of the system. However, for a cyclic process, we saw that work done must be equal to the heat withdrawn, and then from that logic we figured out that when we add these two quantities, the work done and the heat withdrawn, their addition will be always 0, and we got a new quantity which we defined as du. Some textbook write it as dE, E stands for the energy, and that du will be an exact differential because cyclic integral of that is always 0. By cyclic integral, we again mean that we are going from a initial state to a final state and coming back. So, we are following a cyclic process, and during this cyclic process the internal energy of the system does not change or does not follow on the path of the system. Wherever you do a single step compression or multi-step compression, it does not matter. Since you are starting from the same initial state and coming back to the same initial state, it does not matter. Now, we could write this first law in its differential form, in its integral form, and there we write it as U is delta U is equal to W plus Q. Now, we do not write anything delta W, because delta W will mean something like W of state 1 minus W of state 2. That does not make sense, because this delta transfer from some initial state to a final state. Let me explain it further. Now, suppose we make a finite change from a initial state say I to a final state F. So, we will get an integral form of this equation, and du integrated over initial state to final state will be delta u, where delta u is nothing but energy of the system in the final state minus energy of the system in the initial state. Now, when we write the right hand side, I write here as W plus Q, because if I write it as delta W, that would mean the work done in the initial state and work done in the final state, which is meaningless, because work is a form of energy in transit. Same is true for Q, and work and heat are path functions. So, we do not write the integrated law as delta W or delta Q, but for any exact differential we write it as delta. So, we will use this convention where we write the change in internal energy as delta U, but change in work or heat as W and Q, whereas when we talk about the differential form, we write the change in internal energy as small du, and the differential change in work and heat are always written as d cross q and d cross w. So, this is the first law in its differential form, and this is the first law in its integrated form. Now, we have already discussed what is the mathematical form of the first law, and we also had a concept of energy, which is the internal energy. Now, let us suppose that we do some transformation keeping the volume of the system constant. Now, we can write the energy, which we are writing as U, as a function of say volume and temperature.